All right, class, welcome. In our last few sessions, we really dug deep into linkages, right? But what happens when you need a motion that's got to be perfectly precise, something a linkage can only get close to? Well, today, we're going to explore the solution, the cam. We're going to see how these often simple-looking parts can create some of the most complex and controlled movements you'll find in machine design.
So let's frame the core problem we're trying to solve today. This is a challenge that really separates good machine design from great machine design. So let's start with this fundamental engineering challenge. You often need to create these really specific, kind of complex, maybe even weird motions. Now, you already have a fantastic tool for this, linkages. You know how to design a four-bar to approximate a certain path or get an output angle. But what happens when approximate just isn't good enough? What if the design demands perfect timing and absolute precision? More control than a linkage can physically give you.
Okay, so here's our game plan for today. We'll kick things off by comparing cams to the linkages you already know, then we'll break down the two-stage design process, which is super important, and finally, we'll set up the big question that we're going to tackle in our next session.
All right, let's dive into it. To really get why cams are so powerful, we first need to put them side by side with linkages. It's all about picking the right tool for the right job.
So this slide really shows the fundamental trade-off. Linkages are absolute workhorses. They're cheap, especially when you're making a ton of them, but their motion is always fundamentally an approximation. Cams, on the other hand, give you almost perfect control. They can, in theory, reproduce any motion you can define with math. Now, the price you pay for that precision is, well, first, literal, they cost more to make, and second, it's practical. If you don't design them just right, they can have issues with wear, noise, and vibration, especially at high speeds.
And here we're looking at the three key players in a typical cam follower system. First, you've got the cam itself. That's the rotating input that's going to dictate the motion. Second is the follower. That's the output link that actually traces the cam shape. And finally, you've got a spring. Its only job is to keep that follower pushed firmly against the cam at all times. That's what we call force closure.
Okay, this brings us to the core idea behind cam design. It's not just about, sketching some random shape. It's a really structured two-stage engineering process that takes an abstract idea of motion and turns it into a physical part.
It's a beautifully logical process. First, we figure out the motion program for the follower. This is where we decide exactly how we want the output to move, rise, and dwell. Only after we've perfected that program do we move on to stage 2. Generating the physical cam profile that will actually create that motion. Here's the key. We design the motion first, then we design the machine.
So let's zoom in on stage 1, programming the motion. This is where we leave the world of physical parts for a minute and just think about pure function.
This quote really gets at the absolute superpower of cams. You see, linkages are limited by their geometry, right? The length of the bars dictates the motion. But a cam can theoretically reproduce any motion you want. Basically, if you can describe a motion on a graph or with an equation, you can design a cam that will generate it. It's incredibly powerful.
And this graph is our main tool for doing that. This is a follower displacement diagram. We call it the motion program. The horizontal axis is simply the cam's rotation, all the way from 0 to 360 degrees. And the vertical axis is the follower's position, or its displacement. You should think of this diagram as the script, or maybe the blueprint, for the motion we want our machine to perform.
Now, you'll see these three basic actions make up almost every motion program out there. A rise is when the follower moves away from the center. A return is when it moves back in. And a dwell is a period where the cam is still turning, but the follower stays perfectly still. And by the way, that dwell, that's something that's really, really hard to get with a simple linkage.
So this is the million-dollar question in motion programming. Why can't we just connect the start and end points of a rise with a straight line and call it a day? Seems like it would be the simplest thing to do, right? Well, this slide shows you exactly why not. It's all about the physics. A straight line on that displacement diagram means constant velocity. But think about it. At the beginning and end of that line, where it meets the dwell, the velocity has to go from 0 to some value instantly. And what do you know from calculus? The derivative of velocity is acceleration. An instant change in velocity means mathematically infinite acceleration. And from physics, F equals ma. So, infinite acceleration requires an infinite force. In the real world, that means a massive impact, what we call jerk. It causes noise, vibration, and things break. That is why the smoothness of our motion curve is everything.
Okay, so we've designed a nice, smooth motion program that doesn't have infinite acceleration. So how do we actually turn that graph into a physical part?
How do we find the real shape of the cam?
To do this, we use a really clever trick called kinematic inversion. Now, in reality, the cam rotates and the follower moves up and down. But just for the design process, it's way easier to flip that in our heads. We're going to pretend the cam is fixed, and we're going to rotate the follower's path around the cam in the opposite direction. It sounds a little weird, but this mental flip makes drawing the profile way easier.
And here you can see that graphical method in action. Look at the displacement diagram on the right. We take samples from it at regular intervals, say every 30 degrees of cam rotation. For each of those angles, we get a specific follower displacement value from the vertical axis. Now look over to the left. Using our kinematic inversion trick, we rotate the follower's centerline backwards by that same angle, and then we plot the follower's position using the displacement we just read from the chart. We do this over and over for each station, creating a whole series of follower outlines. The final cam profile? It's just the smooth curve that's tangent to all of those positions.
And that's it. That's how our carefully designed motion program, our blueprint, is physically sculpted into the final shape of the cam. The math from stage 1 directly creates the metal of stage 2. It's a really elegant process.
So we've covered the what and the how of basic cam design. Now let's just wrap things up and tee up the next really critical question you're going to face as a designer. So the key takeaways from today are right here. Cams give you precision that linkages just can't. The design always follows that two-stage process. Smoothness is absolutely critical for performance. And we use kinematic inversion to actually generate the profile. The bottom line is that cam design is a systematic process. You start with the abstract behavior you want, and you end with the physical part that creates it. That is the essence of mechanism design.
And this brings us to the really big question, the fundamental challenge of motion synthesis. And it's really the heart of high-speed cam design. We know a straight line motion program is bad, but what about a parabola, or a sine wave, or something called a cycloid? There are literally infinite possibilities. How do we choose the best curve for our specific application? Well, that is exactly what we are going to explore in our upcoming lectures. Great work today, everyone.